Is a lecture over introducing basic stoichiometric conversions, going from mole to mole, going from mole to gram and gram to mole, and then going from gram to gram. And so, quote we have here: one for you, one for me, two for you, one, two for me, three for you, one, two, three for me, by Bugs Bunny. What we're trying to accomplish in this are learning goals that we have. Students will understand the role of the mole ratio. It's a huge concept in stoichiometry. It's what we've been building up to, the mole ratio in stoichiometric calculations. Number two, students will be able to convert from moles of a reactant or product to another reactant or product. So we're going from moles of anything that we have into moles of any reactant or any product. And lastly, students will be able to integrate their previous knowledge of dimensional analysis to include stoichiometry for any reactant and product. So what we're trying to do here is we're trying to include anything that we could possibly have: grams, moles, all of that. So what we already know about dimensional analysis. Now, dimensional analysis is the useful tool for converting between two equivalent values. We have the statement of equality. When we're looking at this, we're trying to convert from 26.2 miles into meters, and so we need conversion factors. We have right here, we have our 1 mile equals 1.6 kilometers, and we have 1 kilometer equals 1,000 meters. Now, both numbers in the vertical column are equal. 1 kilometer equals 1,000 meters, and 1.6 kilometers equals 1 mile. So these equal each other right here. And we set them up so that we can see that their units cancel out. So we have our miles right here, 1 mile, and then we have our kilometers up there. And we see that those guys will cancel, and we get here, we have kilometers right there, kilometers right there. Okay, and we see that miles cancel, kilometers cancel, and we're left with our unit that we want, which is meters. And so we go 26.2 times 1.6 times 1,000 will give us something right around 41,920 for an answer. So that's dimensional analysis. Now, what we already know about chemical equations. Okay, we talked about this a lot in the last unit. It's the law of conservation of mass. So the law of conservation of mass states that you must have an equal number of each atoms before and after the reaction, but they can be arranged differently. So we have to have the same number of atoms, but we can rearrange them. In that chemical reaction, that's what it does. It rearranges everything so we can get something a little different. Okay, now what we learned in the lab, we looked at a titration for this, and we're looking at that titration setup. We used this to figure out what kind of copper or what kind of iron we actually had. The titration is very useful for that quantitative, okay, all those numbers, or that qualitative, we're looking and describing it, analysis. This is very useful in getting the ratio. The ratio can be useful for identifying and predicting reactions. So titration is a very good thing that we use to help us predict what the products are, figure out what those oxidation numbers were, what type of reaction we actually had. So what does the chemical equation give you? Now, when we're looking at it, we look at our chemical equation, and this is a combustion reaction. We have our methane here reacting with our oxygen to produce our CO2 and our water. Well, the chemical equation shows us the mole ratio, and all the mole ratio are these guys up front, okay, our coefficients. Now, our coefficients, see a 2's right there, a 2's right there. If it doesn't have a coefficient, it's understood to be 1. Okay, so when we're looking at this, carbon dioxide has a coefficient of 1, methane has a coefficient of 1. So there's our coefficients, the 1, the 2, the 1, the 2. That gives us our mole ratio. That's the ratio in between them. So 1 mole of methane equals 2 moles of water. 1 mole of methane equals 2 moles of oxygen. There's a 2. 1 mole of methane equals 2 moles of, we have water again, but basically whatever it's set up to, that's what it equals. Okay, so we can also say that the 2 moles of water equals 1 mole of CO2. We can say that our 1 mole of CO2 equals 2 moles of our oxygen. And so everything, all the coefficients, they give us that mole ratio. They set everything up for us. Okay, so using the mole ratio, what it does is it allows you to predict the amount, so the quantitative amount of each product. How many moles of water will be produced when 25 moles of methane is combusted? So when we're looking at this, we have 25 moles of methane, okay, and it wants to know how many moles of water. Well, what's the ratio? We're starting with 25. Okay, we always start with the number that the problem gives us. Well, what's our mole ratio between? We have our methane, so we're starting with at 25 moles, and we're going to water. What's the ratio? Well, it's a 1 to 2 ratio. So 1 mole of methane equals 2 moles of water. Okay, so it's that dimensional analysis set up for us again. We see that they equal each other, and so we just go 25 times 2 is 50, divided by 1 is just 50. So we know that 25 moles of methane will produce 50 moles of water. Okay, let's look at an example here. It says balance the equation below and determine the appropriate mole ratio of moles of octane 2 moles of calcium carbonate. So we're going to have to balance all of these out. The main thing with stoichiometry is it only works with a balanced chemical equation, so we have to start there. So in our first equation, what we have, okay, let's start with our nonmetal, which is carbon. We have 8 here, so we need 8 over there, so we put an 8. Now we have 8 carbons. We have 16 plus 1, 17 oxygens, so that's not going to work for us. So we got to balance out our oxygens. So 17, there's nothing we can multiply, or a whole number we can multiply that to. 2 times whatever won't give us 17, so therefore we have to work it out. Let's look at our hydrogens. Hydrogens, we have 18 right here. We only have 2 over there, so we could put a 9 here. Let's see if that helps us out with the oxygens. So now we have our hydrogens are nice and balanced out, our carbons are nice and balanced out, our oxygen, we have 16 plus 9, so 16 plus 9 is going to give us 25. Still doesn't help us, so let's go ahead and come back and put a 2 right here. Anytime in a combustion reaction doesn't work out for us nice and neat the first time, well, we just come back and put a 2 in front of that hydrocarbon. So now we have our 16 carbons, which now we need 16, so we go over here and we put our 16 right there. Now we have our 16 carbons, oxygens, we have our 32 plus that's 33. Okay, now we have to look, we have our hydrogens, we have 2 times 18 is going to give us 36, which we'll need to go ahead and put an 18 over here, because 18 times 2 is 36. Now let's look at our oxygens. We have our 32 plus our 18, and that would be 50, which we can do that. We put a 25 here. That one was a hard one to balance. Next one, we see start with our carbons. We have 1 carbon right here, 1 carbon right there. That's okay, it's good. Look at our oxygens. We have 2 right here plus 1, so it's 3. We have 3. Hydrogens 2 and 2. So that helped us out. That was nice and balanced. So it's just 1s all the way across. Okay, and then lastly, the last one that we have, we see that we have our 2 carbons. We have 2 carbons right there because that 2 distributes out. We have our 3 plus 3 is 6, which we have 6 oxygens right there. We have our 1 calcium, and we see we have 2 hydrogens, so that's balanced. So really, we only had to balance the first one. Everything else is going to be 1s straight across. So we're looking at what's the mole ratio between octane and our calcium carbonate. So in this series of reactions, what we see is that we have our ratio. We just pick out what we have. Well, here is our octane, which is 2 moles, and look at calcium carbonate, which we have right here, or calcium bicarbonate, which is right there, and we see that it's a 2-to-1 ratio. Okay, so let's look at this A2, example A2. It says write the correct mole ratio for moles of TNT to moles of nitrogen gas. So TNT is right here, and then nitrogen gas is right here, and that gives us we just looked at the coefficients, a 4 to 6 ratio. So 4 moles of TNT equals 6 moles of N2. Alright, next example, we see that we have example A3. It says 35 moles of, we see our potassium permanganate are present in a sample that is mixed with hydrochloric acid according to the equation below. So we have this is potassium permanganate, and we have 35 moles of it. And it wants to know how many moles of each product would you expect. So in working this out, we always start with the number that it gives us in the problem. So we have our 35 moles of potassium permanganate. So 35 moles of our KMNO4. Okay, so what we're going to do is we're going to start every single problem with that. So we set it up. There's our potassium permanganate, and set up our stoichiometric relationship, do our dimensional analysis. So any mole, of our product, we have 1, 2, 3, 4 products. So we'll have to do this 4 times, but we just use 4 different mole ratios. So to our first product, potassium chloride, it's a 2-to-2 mole ratio. So what that means is we have 2 moles of KMNO4 equals our 2 moles of KCl. And then all you do is match everything up. Okay, that's going to go on the bottom. 2 moles of our potassium permanganate, because that cancels out. And then you just put the other part of the mole ratio on top. And so what you'll see is a 2-to-2 ratio is just like a 1-to-1 ratio. So we multiply by 2 and then divide by 2. So our first one will get our 35 moles. Okay, and what we can see is in the next one, it's the same ratio. So it's a 2-to-2. So the only thing that will change is on the top, we'll have our, it's still a 2-to-2 ratio, but we'll have it, instead of moles of our potassium chloride, it's manganese chloride, in particular manganese 2 chloride. So it's MnCl2, but it comes out to be the same thing, okay, MnO4, because it's the same ratio. So this is 35 moles. Okay, the next one is a 2-to-8 ratio. So 2 moles of KMNO4 equals 8 moles of H2O. Okay, so when we're setting it up, do the same thing, start with the same exact number. Okay, and then all we would do is, for dimensional analysis purposes, we put that on the bottom because that cancels that unit, and then put the other part on top. So all you would have here is you would go 35 times 8, and then you go 35 times 8 and all divided by 2, and that will give us right around 140 moles of water. And then our last one we see is a 2-to-5 ratio. Okay, so the bottom stays the same because it's 2 moles of this, 5 moles of HCl. So we just put 5 moles, not HCl, but Cl2 on top. So 35 times 5, all divided by 2, and that'll give us 87.5, and that's moles of chlorine.